Dr. Ralph, he is an advisor of environmental and water at the United Nations Economy and Social Commission for Western Asia. Dr. Ralph has a long history of experience in consultancy services for Middle East, Africa. He is initially trained as a hydrologist and geoscientist, and also he acquired more than 18 years of professional experience in universities, private consultancies, public institutions, advisory services for United Nations agencies and government federal ministries. He has worked as a groundwater specialist and advisor for water and land resources management in Africa, Europe, and Middle East. Welcome, Dr. Ralph.
Thank you, Mr. Chairman. Ladies and gentlemen, thank you very much for joining you today. My talk is going to be with the title Managed Aquifer Recharge, MAR, Regional Overview and Recent Developments. And taking note of the time what I have, I think we cannot go in all the details of all the different developments in the different countries we have, but I think I want to start a bit of a more dialogue here, and we had this already in the last years in each of the WSTA meetings over the last years. Aquifer recharge was a theme, not only the natural recharge, but also the artificial recharge. And I think it is probably worth looking into ways of re-engaging in this dialogue between our countries. But first of all, thank you very much to WSTA and Kachamar and the GCC for the kind invitation to participate today in the 10th Gulf Water Conference. I would like to start, I'm myself from working with ESCWA, and my colleague, Carol Kushani-Jafane, is also here, the section chief for the water resources section, and she will present tomorrow. So if anybody has additional interest in discussion with us, myself, Carol, and also Hanan Atalla will be with us, so we can assist you in any of these questions. What might be of interest to you, is not actually the perspective what Australia has drawn here on this picture, but I thought I start with this. It comes from a recent work on some drought issues, because I think that when it comes to managed aquifer recharge, there's a lot to learn. There's a lot to learn between our countries, but there's also a lot to learn from other areas in the world, and it does not always need to be Europe or the US for everything. There's a lot of experience, particularly on managed aquifer recharge in Australia, and I really would like to invite you to study very well what Australia has done so we can improve our services in the region. Short outline for the presentation. I will go a little bit into reasons for managed aquifer recharge, then differentiating what actually falls under MAR, because I think we all may think of a bit of different things under that. Raise some challenges, actually split up into technology, scientific, socioeconomic, and governance or regulation challenges. Go then into a few examples from the region, definitely not all, and I try to capture as much as possible as easily available and accessible on the internet and from different reports, but unfortunately not everything is talked about, and that is something what we have to talk about. Particularly then also the look into the future, what can be done at regional level and what kind of exchange of knowledge or supporting of each other we can look forward. As you see from the top of the slide, ESCWA has 14 member countries. The Economic and Social Commission for Western Asia includes countries from Sudan to Iraq, from Syria to Oman, and so today we cannot go into all of these countries. We will just highlight a few examples later on. Reasons for managing aquifer recharge, there are plenty. And you can start looking into this from very many different angles, and we will see some of the examples later. Starts with strategic water reserve for emergency situations. It can be for short-term or for seasonal peak demands. It can be used as intermediate storage instead of just letting the wadis run off or the ponds evaporate. It can help in the preparation for drought periods in dry years, prepare for the drought in the good years, and don't start preparing for the droughts when the drought is there. That means it needs a lot of planning beforehand. It can help reducing the vulnerability of kind of desalination to pollution, because we might actually have intermediate storage. We can also look at it from the angle of the aspect that desalination provides us with mainly a constant production of water, but our demands are very variable within the day, over seasons. We can see it in the sense of recharging brackish groundwater reserves, or even preventing or reversing saltwater intrusion, if possible, and controlling soil salinity upconing. Injection of excess rain, storm, and floodwaters, a very different dimension. We're actually now talking not about kind of produced water, like from desalination or other sources, but now we are using the natural runoff and try to encourage infiltration. Additional uses for treated sewage effluent, and we have seen and we know it happens already in the region in many of our countries, but there is absolutely nearly no talk about it, and I think we should actually much more openly talk about it. Otherwise, we will face a lot of problems with our people later on. And the water storage in surface reservoirs and dams, evaporation losses are too high. I mean, we come to that later on in some of the examples where they went into economic analysis between surface reservoirs and surface tanks, and discovered even a factor of 1 to 10 groundwater artificial recharges are cheaper than the overall the options of surface tanks. I don't want to go much into this slide, but I think I just want to use it as a different presentation of the well-known fact that we are, in most of our countries, living already in the sense of very close to the limit of the water resources available. In some of our countries, of course, here in the Gulf, we consume much more water than we naturally have available. That's why we produce it through this desalination. I just wanted to make use of this nice diagram because I think it's a nice way of actually presenting the available and the use. And it shows that some of the countries are actually quite at stress. What falls all under managed aquifer recharge? I mean, I tried to capture it actually more in a very simple statement: human-enhanced and managed groundwater recharge. Now you will say, there are thousands of other things what we have to bring in, particularly also the reuse. But I think the aquifer recharge principle in the first place only talks about the recharge, not necessarily the reuse of the water later on. But of course it goes into why do we recharge, and we only recharge because we want to make use of this water for either abstracting or even using it as a hydraulic barrier later on. Sorry. There is a nice overview and a nice little brochure and documentation from the International Groundwater Resources Assessment Center, the UNESCO Center in Delft, UK, Netherlands, which actually is spread out the different types of managed aquifer recharge. And from this diagram, you see on the top some spreading methods, the technologies. Then comes the green area. This is actually the area what we often talk about here in our region, either the aquifer storage and recovery, ASR, or the aquifer storage transfer and recovery, the deep well injections into aquifers. But there are plenty of other options which also fall under managed aquifer recharge. Even the rainwater harvesting and runoff infiltration through groundwater dams, either recharge dams or subsurface dams. There are plenty of different options, in-channel modifications or spreading methods, which can be qualified under managed aquifer recharge. Maybe one of the simplest, easiest, accessible overview documentations has been done by UNESCO in 2005. And unfortunately, I think you can't read the print on it. But I think there are a variety of different options. What you might see, there are these in-channel dams, what you might see, which can intermediate or intercept the runoff and encourage recharge. There are injection wells injecting water into brackish water or deeper groundwaters, and even recharge into empty aquifers are options. Tools like using water from rivers, surface water, and pumping it into kind of infiltration ponds next to the river is not very commonly used here in the region, but I think at least in the major rivers, we should also rethink in how far we have resources left on the river that we can use from this. Coming back to the main points on this ASR, ASTR, one point is the ASR, the aquifer storage and recovery, means that we use the same wells for injecting as for the recovery. That has an advantage. It saves drilling because you may only need one borehole instead of two. But at the same time, it also helps a lot in introducing and pumping out from the same well, so you actually have a constant in and outflows of the same well, and it minimizes clogging and other problems on the wells. What I think is an interesting option also is the ASTR, the storage transfer and recovery, because it uses additionally the medium of the aquifer as a porous space where you can actually move the hopefully clean injected water, but you can still additionally filter it along the way, that you can ensure at the pump site, at the recovery well, you have an even cleaner well. In particular, when you would have properly set up drinking water protection zones, in case you may want to use this for drinking water or other protection zones, you should use the same kind of standards, of course, for your recovery wells, because you want to prevent that your injections are causing any harm in the downstream recovery. Coming to some of the challenges, and I think that's where we have to go through maybe more in detail. Each of them would have leave enough time for the discussions. Groundwater level rise is, of course, wanted in most of the cases, but we have to be careful that it doesn't rise too high. So, I mean, either by wanted or unwanted infiltration, we might actually cause a risk to flooding, especially in unconfined aquifers. We have the whole issue of chemical mixing, hydrochemical mixing. There are tools available to monitor and model such mixing of waters, and I think it is very wise to use these before you start any pilot schemes or even large-scale injection measures. Because, I mean, on one side you can either have the precipitation or the clogging of precipitation of minerals or clogging of well screens and pore space, or what I think is also something we should not underestimate, mineral dissolution causing either mobilization of harmful substances or the development of cavities in our karst systems and carbonate systems, of course, that is also then an additional risk of failure of the wells later on, or the systems as a whole. The whole system efficiency is an important part I think we have to look carefully in, injected versus recovered well volumes, in particular when we talk about different salinities of injection and what do we expect from the recovery. And then, last but definitely not least, potential health risks have to be well studied. I believe there are enough tools around to apply for these assessments. And despite the fact that we face more and more new and different other pollutants, there is a lot of options to test and evaluate any potential risks, either from microbial pollution or from the mobilization of other minerals. Challenges of the socio-economic viability. And I think that's something what we, particularly myself also as a person who comes from groundwater originally, we may actually often not really see this so much as our worry. And in our countries here, sometimes we also may not really think about if it's worth economically. But I think it makes sense to investigate these options also today, just to make sure that we actually go for the best compromise in the end, look into the cost of surface versus groundwater storage options, using for example, direct use of TSA versus treated sewage effluent versus intermediate storage in the aquifers, using the assessments of what kind of infrastructure is there to access the sites or what needs to be built for this purpose alone. I mean, all this needs to be built into different kind of economic cost analysis, including, of course, the potential costs of environmental degradation, which we actually want to reverse, ideally, from our activities. Again, the system efficiencies need to be discussed also from the aspect of costs, and in my view, I think something what we should not underestimate nowadays anyway in our countries. We are all very much aware that we are not doing this all for fun, but we actually do it for our people. And we actually want to ensure that these people are fully aware of the processes, so that we and actually support our best interest for them in the way that we actually look into health and environmental risk analysis, and use the right way of awareness raising campaigns. And I mean, I don't know who saw that. I just want to use this in the moment because I think it's a very interesting example. Those who have seen some of the papers in Qatar over the last days. This is an advertising. There was two days, there was only half pages in the papers with no information where this comes from, what is this for. And now today we see it's actually an advertising from Kahrama for more sustainable living. Consume wisely. And I think that's a very interesting example of not confronting people negatively, but very positively, engaging people and raising awarenesses for different aspects. Why not also for managed aquifer recharge, for reusing and injecting TSE and other things? Okay, governance challenges, regulations. I think we all have to ask us all the time the same questions. Are all necessary laws, regulations, and guidelines in place, officially approved, to ensure that prevention of negative impacts on the groundwater ecosystems, water users, and the people can be minimized? Accountable and transparent decision-making on and tendering processes. I think I don't have to go more into details. I think all the consultants in the room know what I mean, and the government people probably also. Do we have mechanisms in place to allow for participation and constructive criticism? And another point, is it worth going for international and national advisory bodies, particularly with multi-sectoral experiences in advising our government decisions? Just as an input, because I think all these questions we need to discuss internally in our groups to see how far we want to involve people, can involve people in different levels. Some examples, I go by alphabet, so that starts for me with Bahrain. One example is, I think, thanks from our colleague Noemi, he actually drew my attention earlier already on the Issa Town example of a stormwater runoff system. It's a unique gravity-fed aquifer recharge. They collect through different kind of gullies, catch pits, delivery pipes, and oil traps. They collect the recharge and direct it into the Khobar aquifer. And this publication, they were talking about an injection of about 1,400 cubic meters recharge to the aquifer and a water level rise of 0.6 meters. I mean, the alternative would be to leave this water flooding on the streets and standing, including all the other sanitation challenges related to it. So I think that's a very interesting in-town system. They also, of course, immediately knew there's a challenge, of course, with this. We have to prevent any pollution to the aquifer. And that's why there is also an urgent, there is actually a need to monitor particular harmful substances, particular metals like nickel, zinc, and copper. Another example, I think we don't go too much into the details with this yet because it's still in the planning phases and discussion phases. Bahrain has since many years looked into ways of a potentially larger scale ASR, ASTR options for injecting either desalinated water, surplus water, or treated sewage aquifers, sewage effluent. It started, I think, around 1986, that's at least the information I have, that there were first studies done for TSE recharge into the Khobar aquifer. Later on, and there were many others in between, but I just want to point out the last ones from 2010, because in this case, I think they were done through the Arabian Gulf University with a lot of scientific background, and I think that shows that there is a lot of interest to accompany such studies with scientific knowledge. We see nowadays that actually the government institutions have really joined and really pushed things jointly together, trying to assess better the options for reusing treated sewage and managed aquifer recharge options. I mean, particularly with the perspective of a high TSE production rate in the future, expected to be around 500,000 cubic meters a day in 2030, the direct use on agriculture will be not enough. So there will be a need to think about what is the best option to use this water for. Potential target aquifers are mentioned already. These are both from the Dammam formation. And the overall, as I understand, the overall expected storage amount, what they are looking for, are about 24 million cubic meters, which is quite a sum for a small island like Bahrain. Kuwait, as far as I understand, maybe the country which has started the earliest in already 1964 with some passive infiltration in the northern part of Kuwait in 1972, 1973, also with injection of the desalinated water. Later on in 92, there are additional injection tests. I mean, they're all only tests in Sulaibiyah, more central areas, in the Dammam limestone and in the Kuwait group. These are different injection cycles over injections over 30 days and then trying to recover later on. And they were, in the perspective of these of the publications, they were considered quite successful, although I'm surprised about the low efficiency rates of between 10, 15, 20%. In 94, there were additional studies on the physical properties between the fresh water introduced to the formation water, and also the formations, and also the questions of compatibility of desalinated water with the formation water in pilot recharge areas. There was a lot of work done, I mean, in particular from the Kuwait Institute for Scientific Research, KISR, in combination with the ministries on numerical modeling for artificial recharge, on laboratory investigations, and the latest one, which I just saw then, is a presentation on potential suitable sites for artificial recharge. And that goes actually into an exercise which most of the countries went through. What are the potential best locations from geological and economic perspectives? And that came up with different locations for the Kuwait group and the Dammam formation for Kuwait. Yeah, I catch up, don't worry. One example from a very different region where you, particularly here in the Gulf, probably always think that, this is our water castle. Lebanon will save us all. Lebanon also, of course, understands that their own water resources are limited and are more and more at risk from pollution and overuse. There was a recent study on aquifer recharge in karst, and that becomes more difficult, as those who have been in Lebanon know. The karst in Lebanon is much more developed than in some other countries here. So they went into the assessment of aquifer rechargeability assessment in karst. They called it ARAC. And the idea was actually to try to map in the way of, in combination with vulnerability assessment methods, best locations for potential recharge. This unfortunately has not gone into a test phase yet, but they particularly looked into an area just south of Beirut. And I think the interest is still there to move this further. I have one slide from Oman. I hope you don't mind that I still keep this. This is actually, it's one of the colleagues from the Ministry of Regional Municipalities and Water Resources from a recent visit where we were able to bring a group of Sudanese colleagues to Oman, and thanks again to the ministry for the support in looking into ways how groundwater recharge is organized and managed and implemented in Oman. I took this example from Oman. I could have taken similar examples from UAE, in particular from Saudi Arabia, because Saudi Arabia, I think, has already started in the 50s with similar exercises. It's just this example because I've just been recently there on this one. In Qatar, we've been talking about this, I think, indirectly already yesterday over the food security discussions. Already in 1976, there are USGS reports which go back and state artificial recharge with desalinated seawater to permit additional agricultural development appears technically feasible, and its practicability needs to be examined further. 1976. How far are we gone by now? Do we actually have any implementation of this on the ground in Qatar in the moment? I don't think so yet. I know that we have a lot of additional feasibility studies, and they are all important, but I think we should give this a bit more pace to really get on with implementation on the ground. And I think now with the new strategy, food security program, and the combination of this with Kahama's interest, I understand that there is an interest to find additional storage in the range of 330 billion gallons, 136 million cubic meters, as a long-term security, not necessarily for agriculture, but more as a long-term emergency supply. Yeah, I don't want to go into too much details on this. UAE, I think there are at least two sites which are world known by now, I must say. One is, I start with Nizwa in the smaller emirate Sharjah. I think it's maybe the first operational ASR site in our region, and it started with a feasibility study in 2001 and pilot project and on. Now we are already in the 10th cycle of injecting and recovering water. They have a recovery rate after the 4th cycle of about 95%, which is extremely high. And I think the idea is actually to develop this also in the long run for an overall 1.8 million cubic meter, a different dimension than here for Qatar. Much smaller, but that is at least already implemented. Now here in the other example, what we have from UAE is Liva, and I think a lot of you might have been there already during other occasions in conference in Abu Dhabi. It is definitely worth visiting and looking at the way how that is implemented on the ground. Currently, as far as I understand, we are actually in the construction phase 2010 to 2013. The intention is to have 23 million cubic meter of surplus diesel water stored inside on top of a fresh water lens, which is there naturally already. And this is supposed to help as an emergency water supply for Abu Dhabi up to 3 months with around 180,000 cubic meters a day. They have done a very extensive, you have to finish. 1 minute? 1 minute? Okay. Well, this 1 minute I want to use to this perspective of where we should go and where we may want to go from here. My thinking is actually that we have a potential to work more on these issues. We've done already in the past, but I think we have to reignite our discussions on it, on the technical and scientific challenges. I think there's a lot of experience there, what we should work on and try to improve these, the socio-economic aspects. There are more and more better tools to understand investments in such systems and also the cost analysis for it. So that requires a closer interaction between the economists, engineers, social and natural scientists. More regional knowledge exchange. I think on the regulatory approaches, on the socio-economic, and not only on the technical and scientific. I think there is much more room for learning from each other. Exchange visits between the countries. I think this example from Sudan to Oman was a very successful one, and I hope that actually that leads to additional activities than in Sudan also. In my view, I think it can also help if a particular country goes into a project to look into experts from the other countries and see in how far you can actually draw upon their information in these in advisory bodies. There is a clear need to move from the planning into the implementation stage. And well, I hope I've just ignited a little bit of a discussion, and we may have more time later on. Thank you very much.
Thank you. Thank you very much, Dr. Ralph, and the floor for you.
Thank you. Our second speaker for this session is Dr. Khaled Al-Mashikhi. He will talk about the assessment of groundwater recharge in an arid zone using several approach. Dr. Al-Mashikhi has a BSc in geology and chemistry from University of Qatar, and he got his MSc from University of South Australia in 1997. He received his PhD from University of Jena in Germany, and he is currently working in the Ministry of Regional Municipalities and Water Resources in Sultanate of Oman. Dr. Mashikhi, the floor is yours.
Thank you very much. السلام عليكم ورحمة الله وبركاته. حقيقة أنا سعيد جدا أن أكون اليوم في دولة قطر بحكم أيضا تخرجي من جامعة قطر سابقا، وأبتدي اليوم محاضرتي عن تقييم المياه الجوفية في المناطق الجافة، وهذا كجزء it's a part of my PhD study in southern of Sultanate of Oman. In fact, the study area covers an area of about 88,000 square kilometers in south of Oman, and as you know that the arid zone area is always associated with low rainfall and high temperature. The content of this presentation, I'll give some introduction about the study area and then different evidence that we are using to assess the recharge, and then the results and some summary and conclusion. This is the study area which located in south of Oman, and also the geology of this area, which consists of two main groups, Faris group and Hadramaut group. The second group, which is very important and accounted as an important storage for groundwater in the study area, mainly consists of Dammam, Ros, Radoma, where this, the third one is the important formation for the water resources. In Sultanate of Oman, we classify the hydrogeological or the geological characteristic to 4 aquifers. We mentioned those as aquifer A for the formations above Radoma, and then the other 3 aquifers B, C, and D are restricted with the formation of UER. Also, the formations or the aquifer, first one is semi-confined to confined, and the other 3 aquifers are confined usually in the area. The lithology of these also formations consist of marine limestone related to tertiary age. The groundwater flow direction, it takes the south to north and southwest to northeast, and flowing to the northeast of the study area. And if we look to the formations or the aquifers there, they are, because they are confined, and in that case we can see that the pressure in the deeper aquifer is very high. Even the water strike, if we look to this one, cannot we move the cursor here? If we look, we get the water strike, in fact, in the deeper one, but later on you will see the water level is rise up to exceed also the second aquifer C. And that gave us an idea that there is a leakage between the aquifers, and which might also feeding each other. Here there is 3 evidences we are going to use, cyclone events to compare them with water level in several monitoring water level, and hydrochemistry data, then stable and radioactive isotopes. And that all of these components to see if there is any possibility. In fact, I'm discussing something about the natural recharge. So in that case, we selected several wadi gauges, and then we compared these wadi gauges with the monitoring wells to get any significant rises in these after the floods. And we follow in the network in the area, and we compare it, and later on we get some response in several boreholes. And in fact, we get in the first aquifer, it needs about 7 days to reach the aquifer, the groundwater in aquifer A, and less than 3 months in aquifer B, And then also about 20 days in some boreholes belong to Aquifer C. Probably some others will ask, so why those is around or less than like this? Because we don't have that time data loggers that to say this is the actual time that the recharge reached the groundwater. This is one of the examples we use to compare between the floods and the responding in the borehole in Aquifer A, and we see it's some around 7 days. After that, we conduct sampling in all of the area, and this is the distribution of the sampling from different aquifers, and these are more than 80 samples collected from different places. So we came out as a chemistry with calcium sulfate in aquifer B and sodium chloride in aquifer A, C, and D. But the formations and the lithology there, it's basically in the first part as aquifer B or A mostly consists of gypsum, which can contributed more to sulfate. And we came with this water type in each aquifer. At the same time, we compare also to get any signature or for any tracer of the recharge, which is following any lines. And when we compare this with the chloride, we see that we can get the line which can give an indication for the recharge direction in aquifer. These maps belong to aquifer D, and we see by the chloride, and when we compare that with also deuterium from the isotopes, they are following the same line. Here we plot the stable isotopes for oxygen 18 and deuterium, and we can see in the first group, if we can see, this is the green group. This belongs to recharge area as a monsoon rainfall. But if we look to the other one, the other group also here, which is belong also to cyclone. Oh my God. It's belong to cyclone, and also the most water in aquifer C is belong to fossils water. We compare also the origin of this by carbon 13 as a diox and carbon 14 as a PMC, and we can detect also 3 types of influence: one from soil organic CO2 and atmospheric CO2 in the middle box, and then we can see the carbonate influences in the bottom here, which might related also to fossil water. In the second also comparison between oxygen 18 and carbon 14 as a PMC, we can see also there is 3 sources probably we can detect from this figure, which can give us also a monsoon, cyclone, and also fossil, but also fossil belong more to, and some also probably some mixture between this modern and fossil water. For carbon 14, we try to evaluate also the age of groundwater in the area by using also carbon 14, by measuring by AMS, and also by the other also precipitation. And we compare it also with the noble gases temperature. And we get most of water, the range of the age is belong to modern to greater than 22,000 years. At the same time, we can see also the dots in green. Those shows also that the weather condition in the previous, when it's recharged, it was more humid and cold, and probably the influence of temperature at that time was very low when we compare it with the recent time. Finally, we came to say something about how is this processing is going in the study area. And Based on that, we see that the rainfall comes in the mountain in the south. Some part is going as a runoff, and then the other part is going for the recharge. And most of the recharge occurs in aquifer D at the beginning. And later on, when this aquifer in the previous also filled, then it passed through some faults and fractures to the second layer called aquifer B. And then later on, it passed to aquifer B and aquifer A, getting also some part of infiltration or dewatering from the previous or the bottom aquifers, or also as a direct recharge from the rainfall floods. This probably can be as a reasonable scenario for the recharge in the area. And in that case, we can see also in aquifer C that the water age or the water is belong to be as a fossil. And this probably due to the state or the steady state of the condition of the aquifers in the previous where there is no discharge at that time. And then later on, when we start to bump, we give we give the chance for the fractures to fill the above aquifers. Finally, we summarize some summaries for and conclusions, and that we can say that there is 3 main recharge processing should be taken into account in that area, and modern water by monsoon, runoff and recharge by cyclone events, and also interaction between aquifers due to the hydraulic exchange. Aquifer D probably can nominate it as the dominant aquifer in the all of the study area. Cyclone events could be the first resource for the recharge in Najd, but also at the same time, we cannot ignore also the monsoon. There is probably some contribution from the monsoon, but could be in the second step. Stable isotopes, depletion, and mineralization increases are following the groundwater flow direction from south to north and from southwest to northeast. 2 directions of recharge could be confirmed during this study, and one of them passing through the middle of the study area behind the city called Thamrit, and some of those boreholes can be show the direction of this. By using also the oxygen 18 and the carbon 14, the data also shows that origin of this recharge could be belong to monsoon, cyclone, fossil water. However, fossil groundwater is contributed or concentrated more in aquifer C. Thank you very much.
Thank you very much, Dr. Khalid. You are on the right time. And we hope the other speakers is doing the same, because we have a limited time. Our next speaker is Engineer Abdullah bin Salim Al-Naibi. He has a BSc from Sultan Qaboos University in the field of soil and water in 1992. He participated in many training programs, and he attended many conferences and workshops in the field of water resource management. Also, he contributed in many researches and studies related to water resource management. Currently, he is working at the Ministry of Regional Municipalities and Water Resource as a water resources specialist. Engineer Abdullah, the floor to you, please.
شكرا سيد الرئيس. بسم الله الرحمن الرحيم. الحمد لله والصلاة والسلام على المبعوث هدى ورحمة للعالمين. يسرني كثيرا بأن أعرض ورقة عمل عن استخدامات مياه الصرف الصحي في حماية المياه الجوفية من تداخل مياه البحر في سلطنة عمان. مدينة صلالة نموذجا. طبعا محاور العرض وفق النقاط التالية: المقدمة، ومن ثم سوف أستعرض المصادر المائية في سلطنة عمان، واستغلال مياه الصرف الصحي المعالجة، ومشروع حقن المياه المعالجة للخزان الجوفي بصلالة، ومن ثم أدخل في تفاصيل المشروع ونتائج تقييم المشروع والاستنتاجات والتوصيات. تقع سلطنة عمان في أقصى الجنوب الشرقي من شبه الجزيرة العربية، وتصنف ضمن حزام المناطق الجافة وشبه الجافة، حيث يقدر معدل الهطول المطري 100 ملم في السنة. مصادر المياه في السلطنة: مصادر المياه في السلطنة المصادر الطبيعية التقليدية الناتجة عن هطول الأمطار، المياه الجوفية والسطحية وغير التقليدية، وتشمل التحلية ومياه الصرف الصحي المعالجة والمياه الافتراضية المستوردة. طبعاً هذا عن المصادر الطبيعية بشكل عام. الميزان المائي، وحيث تم تصنيفه إلى استخدامات المياه، وتقدر هذه الاستخدامات ب1430 مليون متر مكعب. المياه المتوفرة 1052 مليون متر مكعب، والعجز المائي يقدر ب378 مليون متر مكعب في السلطنة. استخدامات المياه المعالجة بسلطنة عمان: طبعاً يتم استخدام المياه المعالجة في السلطنة بري المسطحات الخضراء، ويتم استخدامها أيضاً في الصناعة، وحالياً تم استخدامه لمنع تداخل مياه البحر مع الخزانات من خلال حقن المياه المعالجة. مشروع حقن المياه المعالجة للخزان الجوفي بمدينة صلالة: طبعاً تقع مدينة صلالة في الجزء الجنوبي من سلطنة عمان، ومصادر المياه في المدينة تعتمد على المياه الجوفية والعيون المائية ومياه التحلية. السكان يبلغ عدد السكان بالمدينة يزيد عن 140 ألف نسمة. طبعاً استلمت هذا المشروع جهة الإدارة والتشغيل للمشروع، استلمت شركة صلالة لخدمات الصرف الصحي، وهذه شركة عمانية مساهمة مقفلة مملوكة بالكامل لحكومة سلطنة عمان. هذا مخطط عام لمنطقة المشروع. طبعاً اللون الأخضر هي مناطق مدعومة بشبكة الصرف الصحي، واللون الأصفر مناطق مدعومة جزئياً بشبكة الصرف الصحي، واللون الوردي مناطق غير مدعومة بشبكة الصرف الصحي. أهداف المشروع: أهداف المشروع: أولاً للحد من تداخل مياه البحر بالمياه الجوفية. ثانياً التحسين البيئي للمدينة. ثالثاً التقليل من تدهور نوعية وكمية المياه الجوفية. رابعاً تحسين الأوضاع الصحية بالمدينة. موارد المياه بالمدينة: يشكل الخزان الجوفي المورد الأساسي للمياه العذبة الذي يمد مدينة صلالة بحاجتها من المياه، وتعتبر الأمطار خصوصاً في فصل الخريف المصدر الرئيسي لتغذية الخزان الجوفي. الوضع المائي بالمدينة: أظهرت دراسة المخطط الرئيسي للمياه ومخلفات المياه لصلالة وجود عجز كبير في الميزان المائي يتراوح بين 8 إلى 20 مليون متر مكعب نتيجة السحب الغير مرشد، مما طبعاً أدى ذلك إلى انخفاض تدريجي في منسوب المياه الجوفية وحدوث تداخل في المياه، تداخل مياه البحر بالمياه العذبة. نظام معالجة مياه الصرف الصحي بصلالة: أولاً تم إنشاء شبكة التجميع والنقل لمياه الصرف الصحي. ثانياً محطة معالجة ثلاثية لمياه الصرف الصحي. ثالثاً نظام التغذية الجوفية وخطوط نقل المياه المعالجة. طبعاً نظام حقن المياه يتكون من أولاً الخط الناقل للمياه المعالجة. ثانياً آبار التغذية، حيث تم إنشاء عدد 40 بئر على طول الخط الساحلي لمدينة صلالة بطول 14 كيلومتر تقريبا. أيضا تم إنشاء آبار المراقبة، أيضا نفس الشيء 40 بئر، وآبار الملاحظة. أهداف الحقن الجوفي للمياه: حماية الخزان الجوفي من تداخل وزحف مياه البحر المالحة، وذلك بخلق حاجز مائي جوفي هيدروستاتيكي من المياه المعالجة موازياً للخط الساحلي، وبالتالي يمنع زحف المياه المالحة بالمياه العذبة. ثانياً إيقاف أو خفض الهبوط المتزايد لمنسوب المياه الجوفية نتيجة الاستنزاف الغير مرشد. الحفاظ على ثروة قومية كبيرة متمثلة في إنتاج ما يقرب من 20 مليون متر مكعب سنوياً من المياه المعالجة باستخدام أحدث الطرق، وذلك بتخزينها في باطن الأرض. رابعاً الحفاظ على المياه الجوفية كمصدر اقتصادي سليم دون أن يتعرض للتدهور الكمي والكيفي. هناك استخدامات أخرى للمياه المعالجة، وهي الاستخدام الصناعي اليومي لمصنع الإسمنت بريسوت والتشجير والتجميل هدفاً لتحسين البيئة. ثالثاً الاستخدام الزراعي. نتائج تقييم المشروع: الجانب المائي: إيقاف التدهور الكبير في جودة المياه بسبب التلوث الذي كان يتعرض له المخزون الجوفي من تسرب مياه الصرف إلى الخزان الجوفي. ثانياً تلاحظ تحسن مناسيب المياه الجوفية نتيجة للتغذية من المياه المعالجة وانخفاض معدلات ضخ المياه للأنشطة الصناعية. من ناحية الجانب الصحي أيضاً تم ملاحظة التحسن في الجانب الصحي والمتمثل في انحسار معدلات الإصابة ببعض الأمراض. أيضاً انخفاض واضح في انتشار الحشرات، تحسن نوعية المياه الجوفية، انخفاض في استهلاك المبيدات الحشرية، توفير كمية المياه المطلوبة لمصنع الإسمنت من المياه المعالجة. الخلاصة: الفوائد العديدة التي تحققت وراء هذا المشروع خلال فترة زمنية قصيرة فاقت الآثار السلبية كنتيجة للدراسات والتقييم، وإذ تقوم الجهات المختصة دائماً بمتابعة ومعالجة أوجه النقص، وبالتالي ثبوت جدوى هذا المشروع في المحافظة على المياه الجوفية والحد من تداخل مياه البحر. شكراً جزيلاً.
Thank you very much. Thank you. It seems that aquifer recharge has become a very important element in the groundwater, in the water resources management, not only for augmenting the groundwater, but also for protecting the groundwater from seawater intrusion. Our next speaker is Dr. Al-Zubari. He will talk about visibility and health risk assessment of groundwater recharge by TSC in the Kingdom of Bahrain. Dr. Al-Zubari is well known, and he may introduce himself to the audience. We don't have your short CV.
I'm going to be presenting on behalf of one of my students. His name is Aqil Ahmed, and he has finished his master thesis in this topic. My colleague Mubarak was also a supervisor with me, and my Ala. At the outset, let me just give you a very quick overview of what I'm going to be going through. It's going to be a very quick introduction on groundwater resource in Bahrain and development impacts and deterioration of this resource. Then we'll talk about agricultural groundwater and tertiary TEC relationship now. And then we will look at the feasibility of groundwater recharge by tertiary TEC, the methodology and results, and hopefully we'll have some conclusion and recommendations. Bahrain has only one groundwater resource, which is the Dammam aquifer in Bahrain. It is a part of a very extensive regional aquifer that's extended from central Saudi Arabia to the Arabian Gulf waters, including Bahrain, Qatar, and Kuwait, and also Emirates. The water just flows from if there is any rainfall, it will get into the outcrop area, it will flow from laterally with the gradient toward the Arabian Gulf, and then we'll come to Bahrain, which is circled, which is a small part of this regional aquifer. If you look, zoom at this, you'll find that this is the area where the water comes from Saudi Arabia, and then we have two saline or brackish water bodies surrounding the water. One of them is the seawater intrusion, where the aquifer actually outcrop on the sea. And then we have also the brackish water resources. We have been utilizing in the previous 4 decades. There has been a lot of water demands, actually satisfied mainly by groundwater resources. And this heavy reliance has, for 4 decades, over extracting the groundwater beyond the safe field of the recharge coming from Saudi Arabia has a lot of implications in terms of potentiometric level declines and quality deterioration. I'll just give you a very quick example of those. This is just an example of the water level declines of the natural and famous springs in Bahrain. I think Bahrain is sometimes they tell us that Bahrain was called Bahrain because it has the fresh water and the sea water, but I'm not sure about that. But you can see the drop of water levels here. And this is the quality deterioration of the Dammam aquifer. Actually, it is even worse. I think, Mubarak, your map for the last salinity map, I think it's worse than this. We have seawater, we have the fresh water coming from the northwest, from Saudi Arabia, and then we have seawater intrusion coming from this way, and this is why I highlighted in the yellow color. And then we have also sabkha discharge or sabkha inflow, as well as upflow from the bottom. The best waters we have is around 3,000 milligram per liter, which is very, very bad to do. Ironically, our treated wastewater has sometimes better quality than this one. Now we look at the relationship between agriculture, groundwater, and TEC. Agriculture used to rely 100% on groundwater until early 1980s, and then the treated sewage effluent started in a very shy way in certain areas, and then we started to have only treated wastewater actually of a very good quality for our agriculture sector, and it is increasing with time. The reasons are that there is more TSE, there is a huge project of TSE utilization, as well as the groundwater is being deteriorated to a level that it is not usable or it is not good for agriculture. We have one central treatment plant in Bahrain called Tubli. It's the famous Tubli Bay. We'll show you a picture now. The problem with this central treatment plant is that you have a lot of carryovers. The capacity of the treatment plant doesn't, and you have the same thing, Mohammed. all the Gulf states have the same problem, that they have a lot of carryovers, that we have a lot of domestic water supply or consumption goes to a very limited capacity of treatment plants, and the rest where you should do with it, you just have to throw it. So if you look at the inlet, how much water is coming which is the red one, and you'll see how much we have produced and how much we are consumed. You'll see a lot of sea overflow, which is the yellow color. Is it showing here? Okay, it is not yellow here, it is gray. But in my screen, this is sometimes it's discharged to the sea. That's an example of sea discharge. You can see the beautiful color of the green, the green color. This is a raw to partially treated sewage water. So we do have a problem here. The drivers are rapid population growth. Consumption patterns are very high in Bahrain. Bad planning between the domestic sector and the treatment and the wastewater sector. But this actually increases your discharges with time, and because you are having a centralized station, you cannot do anything with it except you treat what you can, and then the rest goes to the sea. That has a lot of impacts on on health, real estate. People who are living there are smelling very bad things. The real estate is going. So there's a lot of issues around that, but this is not our issue. The government is trying to increase the wastewater treatment capacity by increase the capacity, which is centralized. The second thing is to go to decentralization, make another desalination plant away from it, treatment plant away from it, so it will alleviate the pressure on that. And they're also thinking about cleaning up the place, and there is also a thinking of putting a tariff on wastewater, but actually, I don't think it is going to work. So, with all this thing, looking at this system of waters here and there, why don't we think about MAR? Managed aquifer recharge. Why don't we think about taking this water and trying to treat it to a level that it can be useful for the future instead of throwing it? Because even if it is secondary treated water, it is still expensive. It's about, per year, maybe it is around $250,000 Bahraini dinars, or sorry, $250,000 that has been thrown into the sea as secondary treated. Why don't we just try to think about it? So this is one is kind of a scooping study to potential. What can we really do with this? We did not do the actual recharge, but we did all the necessary steps to do a pilot study for recharge. So this study, but how about looking at this water from an integrated way? Instead of throwing it, why don't we just treat it and put it in the ground? We are sure about the hydraulic benefits in raising the water level. We are sure about the salinity benefit because the groundwater is very bad in terms of salinity. But how about the health risks when this water goes down there and then we use it for drinking by the farmers or something like that? So our objective is to find the best location in Bahrain that satisfy that operation. Very quickly, the methodology has, we have to make a site selection using a GIS tool, but it is a matrix, a criteria matrix to rank the best location. Then we do have to do simulation modeling for the groundwater system and see what is going to happen if we inject this much, and what will happen in terms of quantity of water level as well as in salinity. And then we have to do the health risk assessment of what will happen if any viruses like pathogens, go to the stomachs of our people. At the same time, we would like also to look at other things other than viruses, maybe nitrate or something like that. And these are, I have listed the tools that have been used. They are not important. But we started with a site selection. Now this is the result very quickly. We looked at all these criteria. And at the end, we have located 2 sites in Bahrain that are suitable for. Now this is just the first step. Then we have to go and really analyze if this is really works or not. So we started to simulate this region, the western region. This is the water levels, this is the salinities, and then we looked at what is happening to the treated wastewater. Treated wastewater, some of it used, some of it discharged, some of it not treated, and all these things. So the students have developed 6 scenarios. They are very simple scenarios that to make artificial recharge as a national planning thing. It's not an ad hoc, it is really a national plan where you're going to take everything, treat it, and inject it. Okay, that just give you, this is the maximum that you can do, and then we go down to the practical solution. Either you take the storage tank and put the extra, put it here and here in halves, or you put it all in one place, or you put it all in another place. All these things are the scenarios, and we have 2 locations called Dumistan and Malikiya. By the way, Malikiya is where Turf ibn al-Abd is, was living in Bahrain. This is a very historical, region. So we started the simulation modeling for the hydraulics, the hydraulic advantage. The hydraulic advantage, all the water levels have shown a beautiful increase in water because, very simple. You have water, you inject water, it has to go up. And you have a lot of farmers surrounding it, they are pumping it, actually, okay? So that's why it goes down with time. But there is a benefit, of course, than not injecting. And then we looked at the salinity, what will happen. So you can see the freshwater bubble of the treated wastewater is better than the groundwater in terms of salinity. So you can see the bubbles are, expanding with time for each scenario. But this is, of course, the best. We are talking about this one. This is the best scenario where you have to inject a lot of water. It makes a larger bubble. This is simple. You don't have to be a nuclear physicist to reach this conclusion. But then, what can we do about the health risk? That was our worry. So we have looked at the pathogens. We have used the 99% removal rate, which is 200 days for the worst pathogen we have, and we started working on that. So we injected pathogens, theoretically, of course, and all the scenarios, and we looked at where it's going to go. We have two concerns, actually. The two concerns are the farmers' well, which are surrounding the sites, as well as a domestic well field that is used for blending with desalinated water to go for the houses. So our concern is to go, these things has been the criteria. If that injection within 200 days will reach anywhere. And this is what we have started to do, looking at this. So this is the domestic well field, and you can see the scattered farmers' wells. And these are the two injection wells and all scenarios. And we found that this is the best scenario, that this has the minimum, because it doesn't go to the well field, but it goes where? To the farmer's well. So here is where you have the problem. The farmers, if they're going to be using this water for drinking, because it's going to go inside and come back. While the one they are using directly from the government lines, they will not be drinking because they know it is coming from the government for wastewater. So this is probably will need, if you're going to implement, you will need to go for an awareness program and showing. And here where you go with the stakeholders, stakeholder awareness and participation. We also thought about the nitrates. How about the nitrates? Nitrates are a little bit dangerous, okay? And they are there already. But when we looked at the nitrate, they were less than 10 milligram per liter, which is below the maximum allowable limit for, for babies or for humans. So we said it is less than 6, but then we went and searched for in the literature, and we found that some of the literature saying you can, yes, 10 milligram per liter is dangerous, but if you continue having a lower level of nitrate for a long time, it can also cause cancer, even because the doses. It's not the level, but if you go to a lower level. And then we said, okay, let's look at it again. So we started modeling nitrate and how the plume of nitrate was going to move from one area to area. And this is what we started to see, that the nitrates are going to expand with time until they reach about 4 kilometers bubble. If you go for the best case scenario, which is injecting around 70 million meter cube per year inside one location. And this is, of course, going to happen because you are using it already. But this is the worst thing, that you will have 4 kilometers buffer zone, that you make sure that nobody drinks that water from the farmers, because you'll be injecting it. Yes, they are using it on the ground directly for irrigation, but if you inject it, it might come back to them. And we think this is ASTR. Still, we have to be careful. My main conclusion is that we still think that artificial recharge is viable. Actually, is the only option for us for supply augmentation. I mean, we are doing desalination, but this is the best way to enhance your storage. And we recommend that there's a field pilot study to be done in the location that has been decided, and then all these results has to be validated by actual numbers. There's a lot of things, and the next stage should be a stochastic modeling, actually. But we did not do that. We just want, we did everything in deterministic way. We think MAR should not be looked at as an ad hoc. If I have extra water just there, it has to be within a plan, a completed plan, with all the ministries involved, with all the stakeholders involved, and then develop a 3D simulation model to carry out your groundwater management and including your artificial recharge. And thank you. I'm sorry if I took more time.
Thank you very much. Thank you.
Okay.
Thank you very much, Dr. Walid, for your time management. And actually, we are thanking all the speakers for their valuable presentations, and also many thanks for the audience for their attention and patience. In fact, we live in very scarce area, scarce of water area, and we need to do more efforts in the cooperation of legislation and regulation plus new technology. And I think we need to support the researchers for their efforts, which can come with some ideas. It may help to minimize the gap between the demand and supply of the water resources. Actually, the speakers present many case studies, and also they show that there is a potentials for overcoming the many problems in the area, and we hope that will be successful. So now we're coming for the questions, if there is any.
We ask for the researcher now, the speaker,
Yeah, the speaker to come. Yeah. Okay. أربعة.
Only 4, it's enough, I think.
Okay, please, Ben. Please, come.
My question is related to the talk of Mr. Mishikhi. Is here.
Sheikh.
Okay. You talked about scenarios for recharge of 4 aquifers, A, B, and C, and D. And you talked about resources based on isotopes data. Did you calculate a mass balance within one aquifer, and also mass balance to show, because you talked about recharge from D to C to B and to A. Did you calculate a mass balance to justify this scenario? Clear? And second question, what do you mean by noble gas temperature? Yes, noble gas temperature. Yes. So.
This is the first question that I didn't involve in the water balance. I'm basically following something to see if there is any possibility of recharge by using different methods to see if there is any possibility. Because this could be the first study taking care of all the aquifers separately. And in that case, we follow just to find if there is any possibility or not. But as a water balance, there is another study conducting in the same area now. It's a study also for a PhD student, and it's running, it's on the way.
Even in terms of chemistry, balance of chemistry, you talked about recharge from using, for example, major elements, using trace elements to show or to justify this connection between the 4 aquifers and the input from the 3 sources. Not only in terms of hydrology, even in terms of chemistry. Yes. Okay, later, we will discuss later. Yes.
For aquifer D, that's why we said that it's from aquifer D more than others, that the recharge of the water is coming from aquifer D. You mean that?
Yes.
In fact, if we look at the data itself, we saw that aquifer D gets more recent water, more than C. So, which gives us an indication. The second thing, aquifer D is distributed in all the study area. However, aquifer C is started from 80 kilometers offshore. It doesn't distribute it in every way. And that's why. The second thing also, aquifers A and B also restricted in some places and not distributed everywhere. So sometimes if you look to the mountain in the south, and the area close to the mountain from the north side, you have several boreholes to dig in that area, but we detected aquifer A or B or C. And that means we need 50 kilometers to pass north, and due to the high pressure, even in one figure, I have seen shown from one figure, there is a pressure of D Even the water cycle is deeper, but the water level is rising up, which gives us an indication that this reading is coming from there with supporting of the data that's from isotopes.
Thank you. Annie? Hilal?
For Dr. Walid, if we use this amount of water we are recharging directly for agriculture or for other purposes, can we save the aquifer from drawing down? So, I mean, we just compensate for instead of drawing it, we just use it directly since we are treating it to the tertiary level. So maybe that can work in that way. Thank you.
The problem is that we do have a plan for utilization, but there's always sometimes we have a lot of samples that you cannot do, you don't know what to do. Okay, because of lack of pipes or the plant has not reached it. So what they do, they treat it and then throw it to the sea. But there are plants and they are moving, but they are very slow compared to the amount of water that's coming. And that because we feel like there's a lot of forces here. You treat and you throw, and there's a need. So why not store it for later use, as well as help the aquifer to recover? So if it is up to me, I would like to use all the water on the top. In the surface, why should I increase? But if I have a surplus, I would like to not to lose it and keep it for another season.
Okay, the gentleman over there.
السلام عليكم. السلام عليكم. My question for Mr. Mahmoud and both Dr. Walid. Both maybe. Yeah. You've mentioned, or before Dr. Ralph mentioned, there is a problem of blocking due to accumulation of total dissolved solid. So did you observe this? Or maybe in the long run, after few years, this problem will come up? And the accumulation of nitrate, Dr. Walid, you mentioned the accumulation of nitrate. Maybe does this because of the selection of the site? Maybe the gradient of water flow cause this problem. So you said the nitrate is little, but it accumulates on long time. Maybe is this because of the selection of the site cause this problem? And Mahmoud, Mr. Mahmoud, شكرا على الورقة الجميلة اللي قدمتها. لكن هل برضو شفت accumulation ل total dissolved solids ولا start to block the pores of the soil? شكرا.
Abdullah.
Question, yeah.
No. Two questions, one for you, one.
May I just ask he did not understand the question. He's a German. But can I just ask, looking of wells or pore space, necessarily relate only to the aspect of the lowness of solids. I think there's often related either to air in the water of injection. I think it was the case in Kuwait, one of the studies, and also due to systemic solids which are then going to well streams or mixing this water with other water from the active material. So actually that leads to precipitation of minerals in the near vicinity of the well. So that can actually cause becoming. I don't think it's necessarily related to the quality of this concept alone.
Yeah.
It's more the different mineral compositions when you have water mixing together. And that's why I think there are tools, 3D and other modeling tools to model hydrochemistry of mixed waters to find out what actually happens at the moment when you mix different types of waters. is tools to prevent such things to happen?
I'm not sure really about the question about the nitrate, but let me explain what we have. We have nitrates. We have nitrates level less than 10 milligram per liter as nitrogen. Normally, when it's above, I mean, when I want to model, I want to know where the nitrate will be reaching the 10 milligram. But I start with injecting water with less than 10 milligram. So the simulation becomes meaningless. It's immaterial for me to do anything. But then when we went to the literature about the dangers of nitrate, we realized that the nitrate, if you did those small doses of nitrate, less than 10 milligram, for long term, they still cause health risks in terms of cancer. So we just modeled it for the sake of modeling and seeing what will happen. Now, why the nitrate is less? It is desalinated water mixed with human excreta. So why is that? I don't know. That's a little bit long. Did I answer the question? Or maybe we can do it and we can discuss this later.
Yes. Okay. The gentleman over there. Yes. I think.
Thank you. I think this is a very important aspect of recharging water using treated wastewater. I'm very happy that we're thinking about this and studies undergone. And as has been already said, it's the best way of storing water. Maybe here you have the problem of overproduction, but sometimes also during the rainy season in some other Arab countries, what you do with this water, if you can store it, this is the best way to do it. My worry is, what about micropollutant? This is where a lot of work should be done, I think, because micropollutant, like pharmaceutical product, those things, and those could be dangerous for potable water, not for agriculture, but for potable water could be a very high risk. Thank you.
This is
maybe
this comment.
I think it's a big challenge. I think it's only a challenge for TSE reuse and injection. It's already a challenge for groundwater all over the world now. The more developed the countries are, the more they face problems of micropollutants, particularly from pharmaceuticals, in traces in their water supplies. Of course, we have to address the source of pollution, but we cannot prevent that actually still there is something going into the systems. The more, I mean, that's why I think the more we look into ways of encouraging not the same well to be used for injections and withdrawals, the more we have chances to have the additional filter of the active material. Still, we cannot prevent that it doesn't go through, but at least we have additional filter materials in between our injection and recovery. That's one of the steps. Still, on the process side, we have to work that we have the best water for the injection in the first place, and that we prevent the worst of the some injections to the worst pollution to take place in the case.
I can add here very quick. I mean, if you look at the wastewater starting from where it is coming from until you use it, there's a lot of bad players in the middle. And you have to really minimize the risk from each one of them. For instance, if you have a very bad land planning and zoning, you will be putting waste. I mean, you put industrial waste in the middle of domestic waste, and this goes to wastewater. If you have a very unaware population and they throw everything in the sewage, also you will have this kind of problem. So what you do is you have to go through the system from A to Z to make sure that the operation or the minimizing of this at the maximum. This is very important. You cannot just use it. I mean, and if you want to use the water, there should be another unbiased agency to come and check on the water before you use it. This is what happened here in Doha. So this is a lot of legislation and technical innovation need to be looked at you talk about microbes, we have also other concerns. Actually, we're concerned about the chemical reaction between the water that you inject with the aquifer, and they might even clog. So there's a lot of studies. This is why we are hesitant in doing this. We are just doing experiments, piloting, scooping. But I think maybe the next conference will be courageous enough to say we have done something.
Okay, one final question from this side.
السلام عليكم. خالد بطاشي من وزارة البلديات الإقليمية وموارد المياه سلطنة عمان. سؤالي للدكتور وليد. You speak about discharge water or treated water in the sea. Do you have any regulation, health regulation or environment regulation to discharge that water or treated water to the sea? And what is the environmental impact in the living, which is like a fish or all kind of animals in the sea? Is there any assessment or study to that environmental impact that living beings?
Bays we have. It's actually where all the fish and the shrimps hatching today. The losses are not only on the environmental and ecological system, it's also on the real estate, on the lost opportunities for tourism, so many things, and this has been already affected with a lot of losses. There's a fish kill phenomenon that's coming every day now and then. This is a good indication of how much you are losing from your fish stock. So there is a lot of studies, and if you want, I can provide you this. Actually, my colleagues at the university are doing this, and I'm very committed to it.
Okay, thank you very much.
Okay. Thank you very much for the all, and I think it was very interesting session. And we now invite the speakers to present some presentation for them. Please come. Yes, come please.
For the chairs. لا والله ما خلصنا. لا والله ما we would like to present to our co-chairs, a certificate of gratitude, and Dr. Ahmed Khater, who is the honorary member of WSTA, will be doing this.
Dr. Mubarak Kaman. Thank you.
Excuse me, Mr. Ralph. Hi, how are you? I'm